Hello guys, I hope everybody's doing well and are ready for lecture today. Hello guys, I hope everybody's doing well. We're ready for please remember to check in, and once I see a few of you on chat, I will make some basic announcements. Yes, good morning to you too. I hope all is going well. I was just putting the final touches on the policy book for you guys, making the changes in terms of curriculum maps that you, for the most part, don't really care about, but that the college cares about. So, as such, it has to be in the material that I give to you. Let me fix that. Thank you, Nicholas, for letting me know that the attendance form, I forgot to reset the end date. I'm going to unpin this other one, pin the new link, and make the change in Teams. But thank you very much, Nicholas, for letting me know that there is a problem. And that's exactly how you should do that. Anytime you run into a problem, it's probably something as trivial as me having not set a me having not set in or adjusted a date time before I created the link. So it's not something that's going to be horribly difficult to fix, but it's just something I need to know needs to be fixed. So thank you very much. That should be fixed, and you should have the ability to check in now. Yay! Isra, I can see every question you ask in chat, and I will certainly answer those questions. And those questions do count towards your participation in questions and answer, because I do go back through and look at the live chat and see who participated and asked questions if I can recognize your name. If you are chatting in live teams without where your name is not an obvious name, then just chat me in Teams. As a personal chat, don't put it in the group chat, but as a personal chat just to me, and let me know what your YouTube handle is so that I can associate the questions you ask in live chat, or later when you go back and rewatch this, if you go back and rewatch it, to your questions grade for the course. I don't have a problem doing that. And this is in fact one of the ways you get those credit for asking questions in the course. Now, I'm about to swap over week 2 questions and answers. So I just posted in the questions and answer the divide for week 2. Now, in terms of the calendar, I didn't have, this is the first week where questions and answers matter. In other words, this is the first graded week, the first week where everything is supposed to run as a unit and as a whole. And that's because at this stage, late students coming in and being registered or being added to the course should be at a minimum. So we should be at the stage where I can start assigning homework and students aren't going to have to catch up, and so on and so forth. So we should basically be at the stage where everything runs smoothly. Now, that means that in terms of your calendar, I do need to update it because I had forgotten about that. You'll see that the first week 1's participation in questions and quiz will be due on Sunday of this week. Bonus and homework 1 is due this week. So let me quickly talk about where to find the homework and then go from there. The forms should be fully available at this point where you can ask, where you can check in. Now, themes. So, coming back to teams, you have multiple channels. The question and answer channel is the channel where you should ask questions. You will receive credit, and I want this very clear, you will receive credit for the questions you ask in this question and answers channel or in the live streams of the chat. So in the chat of the YouTube video, or if we are meeting in person, there will be a bucket that you can drop a question in. You'll have to write your name on it. Those are the only ways that you will receive credit for questions. A lot of you have been asking questions in the general ask everybody a question in Teams chat. Those questions do not count. That was a way for me to contact everybody about like an emergency announcement if we were scheduled to have an in-person class and because of family issues I had to make it online. That's where I will post that stuff along within Teams. But I am not taking questions there because there's a specific channel called Questions and Answers in the team for you to ask your questions. And that's where you will be graded for your questions. So, just wanted to get that out of the way since this is the week when I start counting questions for a grade. This is where you post them. Somebody asked, well, what if I don't have any questions? You've got to have some questions. I'm sorry. Everybody's got questions. It doesn't have to be directly related to the material, but everybody has questions about chemistry. If you don't have any questions, it means you're not understanding the material. So just say, I don't understand this. That's a question. Or you're not thinking about the material, or you're not reading the way you're supposed to be reading. I cannot cover all of the material in this textbook. I am here to cover the material that is either confusing or to go over concepts where students get in trouble. But general definitions, I'm not going to post a slideshow on general definitions that you can get from reading the textbook. And that leads to the homeworks. In other words, you're supposed to read the textbook. And that's going to be true for those of you that are just starting your college. That's a true assumption for any course you take at college. We are expecting you to read the textbook and the readings that we assign. And you will be tested on that, whether or not we talk about it in class or not. Now, I'm going to do one additional thing real quick. There we go. Because somebody asked me for this, and I definitely do need to have it posted. Save. And it leads to the final thing that I need to talk about before we talk about homework. Okay, that takes care of that. General channel, shared, class material. Now I will post the suggested bonus one problems this afternoon. I don't have it at home. I've got to go into my office to have it. Course policies, and while I'm at it, you will get an updated version of this data booklet on Wednesday when we meet in person. And you'll get the course policies booklet as a hard copy when we meet in person. But they are now available. So, somebody asked about syllabus. The syllabus is a combination of these course policies, which are true held across everything, the official course calendar, which I need to update. Now, so I've just updated the course calendar. Let's see if it links to the new updated. It does not. Okay. Close. Course calendar. Sometimes you hope it updates something and then it doesn't. It's typical. Okay, so updated course calendar is there. You'll see when the assignments are. That somebody was asking about that. What's our first graded assignment? There it is. If there's a red box that you check, that's a graded assignment. Told you I just updated the calendar, and I posted in the chat that there was no assignments. That somebody asked about that, and I posted that information on Friday or Saturday. Somebody asked about that. Okay, so course policies, course calendar, course assessments, and grade scale. That constitutes your syllabus. And all of these you can print out. Course policies is this massive booklet. I do want to point this out because somebody else asked this. This is a 4 credit hour course. Because it's a hybrid course, the hours that are given are a mixture of lecture meetings and readings and so on and so forth. But I am supposed to be, as a hybrid course, providing you 180 hours of learning time. And that means 13 hours of lectures, reading, problem solving, and homework per week. Legally, that is my legal requirement to provide to you by New York state law for a hybrid/online course. Just making that clear so that you know what this course is going to require. Now, in terms of links, we now have a Homework 1 suggested problems. This is all from Chapter 1. So Chapter 1 suggested homework problems. It's from your free book. It's from the OpenStax textbook, which is why I could just do this and not have to type them. There's a lot of problems there. Not all of you are going to need to work all of these problems. So if I go look at the Chapter 1, which is Essential Ideas, homework, what you will find is, for instance, problem 27 and problem 28 are identical to each other. Classify each of the following changes as physical or chemical. Classify each of the following changes as physical or chemical. If you understand that concept after working problem 27, don't work problem 28. If you're still struggling with that after problem 27, then work problem 28. So the idea behind this is I gave you both problems, because each and every one of you is going to learn this material differently. And each and every one of you as a person is going to find certain things harder than other things. I can't predict that. So you're going to have to judge how much is too much homework and how much is just the right amount of homework. Now, what I've given OpenStax, one of the nice things about the textbook and also one of the problems about the textbook is it is a try again, Nicholas. So what is it likes about the textbook and what it try again. What it likes about the textbook and what's the problem with the textbook is it doesn't have any extraneous homework problems. So a standard freshman chemistry textbook is going to have about 200 homework problems at the end of the chapter. And OpenStax textbook has about 100. So in other words, they got rid of a whole bunch of problems. And that means that when I put a suggested problem list, it's going to be pretty much most of the end of chapter problems from OpenStax. And that's because they've already narrowed down the list of problems to about as small a list as you can get. If you're still struggling after doing the OpenStax problems, then you might go to your other textbook and see if you can find other homework problems that are similar. And there will be some that are similar. I just decided to use the OpenStax problems because then I don't have to wait on you guys to get your own individual textbook and so on and so forth. And that's particularly true this week. Now next week, and also because for you guys, the guided inquiry textbook doesn't actually have an activity until chapter 2. So the chapter 1 material, they did not write that type of activity for. So we won't hit the workbook activities until next week. So that's an advantage to that. Now here's how this is going to work. So I'm going to show you an example from last semester. So last semester I would assign a series of activities, and then I would come in and hand out something like this in class. So for this activity exercise 1, answer this question. For this activity exercise 3, here are the questions. In other words, I was pulling questions directly from, you probably couldn't see that because I wasn't sharing my screen. Let me explain. So, in essence, what I'm going to do is I'm going to go through the suggested homework problems. So on Wednesday, you guys will be handed a paper. And because we're meeting in person for the last hour of class, that's how this will work. You will be handed a paper where I have gone through these and I have just randomly pulled an exercise and I've asked questions based on that exercise. And it'll just be random. I'll go through here and randomly pull certain qualitative, certain quantitative questions. It'll be a fairly broad selection of those. It'll be enough questions that if you've already done your homework, you can just write your answers down on the sheet. And if you haven't done your homework, you should be able to complete the material in that hour if you have studied and you know the material. If you don't know the material, i.e. you attended this lecture, you wrote some notes, you didn't go over it, you didn't try to do any homework before class on Wednesday, you show up at class and you're handed the sheet, you're not going to finish it. And then you'll have to just take it with you and you'll submit it Friday, but you'll be charged a late submission fee. In other words, I will take off 2 points of the points because it was late, submitted late. So, you'll notice like on exercise 93, 94, 96, it just says Kelvin in parentheses. That's because the temperature is already in Celsius and it asks you to convert to Fahrenheit or Kelvin. The truth is in science today, we don't use Fahrenheit, ever. So, I am not going to be asking you to convert from Celsius to Fahrenheit. Now, exercise 95, you're given something in Fahrenheit and asked to convert to Celsius and Kelvin. There you do need to know how to do it, because there will be instances where because we are in the United States, where you are given a temperature in Fahrenheit and you do need to know how to convert it to Celsius and Kelvin. A lot of the stuff we do, when we're taking temperatures in the lab, we use Celsius for most things at room temperature or high temperature. When we go to extremely high temperatures, we still tend to use Celsius. When we go to extremely cold temperatures, i.e. negative Celsius degrees, we tend to swap over to Kelvin. Why? We don't want to write the negative sign. And Kelvin doesn't have a negative sign. So if you're like working with liquid helium at 4 Kelvin, you don't really want to write minus 268 degrees C all of the time. So you write 4 Kelvin. Now, when we start doing thermodynamics later in the semester, everything has to be in Kelvin. So you do need to be really comfortable converting between Celsius and Kelvin. Being comfortable converting from Fahrenheit to Celsius, we're not going to ask you that. I'm not going to ask it on an exam, and I'm not going to ask it on, it won't be on the final. Because we just don't use Fahrenheit in science as a temperature scale. So I'm not going to require you guys to know that because we just don't use it. If you need it, you can look it up, in other words. Okay. So that's your homework. And that's how I'll basically just be randomly selecting problems. Now, you will notice in your chemical literacy, there's the optional body doubling work along in office hours. You'll also notice that appears in the calendar for tomorrow from 8 p.m. to 11 p.m. There will be another one of these on Thursday. I haven't set it up on Thursday because I have to live stream tomorrow so that I have the template, and that'll make it easier to set up in the future. So that's why I have the Thursday one's not on here yet. It'll go on Tuesday night. But during that time, I will be working solutions to these same problems. And I'll be typing up the homework for Wednesday, and so on and so forth. So in other words, I'll be doing my homework and listening to some music while I do that. And if you guys want to join in where you can ask questions as you do your homework, that gives you a 3-hour study time set aside to study along. That's what that's there for. you're welcome to join. Is there anything else I need to go over in this regard? Oh, I do want to see. Now, one of the mistakes that's commonly made, I'm just checking the end of you have the whole textbook. A lot of the problems have answers in the back of the book. That's what I was checking. Now, those answers aren't solutions, but because a lot of the problems have answers, when I write solutions, I'm probably not going to write the solutions to all 100 problems I posted. I'm going to write solutions to, like on questions where there's two questions that are identical, I'll write the solutions to one, and I'll actually check and see which one's not answered in the textbook and which one is answered in the textbook, and probably write the solutions to the one where the textbook provides an answer. And that has to do with copyright. But that does go in line with what's the difference between an answer and a solution. So solution takes you through these steps to get to the answer. And this is where I see students get into a problem with AI. So you could certainly plug in, you have the PDF, there's no issue, you could plug in that PDF to ChatGPT and tell it, please answer all these questions for me. And it'll provide the answers to all those questions, because this is general chemistry. There's no mystery about that. And then you can sit down and go about trying to memorize all those answers. What's going to happen if you do that is you will flunk, and I do mean flunk, the exams, every exam in this course, because you don't know the answer. You don't know how to work the problem. And because when I ask questions, and this is going to be true for both the homework and for the exams, when I ask questions, I'm going to be asking you to work your way through the problem, not just work the problem. Now, because I'm going to get asked this, and I'm going to go ahead and do it. New folder. Old exams. Okay. I'm going to upload to you guys examples of the old exam and the and a practice final. And some old quizzes. Now, obviously the course has changed in terms of setup and stuff like that, but this gives you some kind of an idea of how I ask exams. So you can see kind of how I walk through and ask questions and divide questions up. There's multiple versions. And it also gives you some sense of what the type of quizzes you might see in terms of multiple choice. So that is now posted. You can get to that from general shared, class materials, old exams. So that'll give you an idea of the way I take an homework problem and convert it to an exam question, And you'll see some of that on the homework questions too. But in essence, what I do is when I sit down and work out a solution to the homework, then when I write a question, I ask a question for every single step I had to do to get that solution. And since I assume that that's what you would have to do to get the solution, that's what you should also have in your notebooks. And generally speaking, if all you do is write an answer and all you know how to do is get the answer, you're going to get 2 points out of 20 because the answer is worth 2 points. It's how you got to the answer that's worth the larger percentage of points. So just wanted to put that out there and go ahead and state that. We're at the end of our first Pomodoro. So, are there any questions? You can pop them into the Teams question and answer. If you don't want them to be live, I am going to put the break count on. So you can ask your questions in the live chat or in the Teams question and answers in the main channel for Teams. So you should have a question and answers on your channel. So has everybody, while we're taking a break and I'm waiting on questions from you guys, I do see a question from Ethan that asks, are you allowed a cheat sheet or anything for the exam? So, I'm going to flip back to Teams for just a minute to answer that question. So, in terms of cheat sheet, what you will be given on Wednesday evening when we meet is you will be given this data booklet. Now this data booklet is, oh, I put the Word version, I need to put the PDF. This data booklet, when I print it, is a folded, stapled little booklet. It's a half-page booklet, so take a 8.5 by 11 sheet, fold it, and it's stapled together. That you are allowed to write anything you. This is the booklet you will use for all of our exams. That means you can write anything you want in this booklet and use it. The Word file is definitely off. I'll put the PDF for you guys. And there's even a place for your notes. And I'm not checking it. You must have your data booklet for the exams. If you forget your data booklet, there is a table upstairs on the second floor that will have all of the papers that are handed out for this class will be on that table. So if you ever are missing an assignment or didn't come to class or anything like that, that's where you go pick up your stuff, and there will be extra data booklets on that table. So if you forget your data booklet for the exam, you can go get one. So you can write notes in that. I'm not going to check it. Now, on the final exam, you're not allowed this data book, and you're not allowed a cheat sheet, and you're not allowed any data's going to be provided, the exam's going to be provided, an answer sheet's going to be provided. All you are allowed to have with you for the final is a calculator, non-graphing, non-programmable, and a pencil or pen for my class. Pencil if you're doing Scantrons. But that's it for the final exam. So no cheat sheet on the final exam. But for the in-class exams, you can write whatever you want to in your data book. That's whatever you want to have. Flip that to breakout just because of private. Emily asked if all of the homework right now is coming from OpenStax. Eventually there will be questions coming from Chemistry, a guided inquiry workbook that you're required to purchase. But as I stated, there are no activities associated with this material in that workbook, which is why you haven't been assigned an activity out of that workbook yet. As soon as we get to Chapter 2, that changes. But for Chapter 1, there are no activities in the Chemistry, a Guided Inquiry workbook. So that's why all of the homework for Chapter 1 is out of the OpenStax textbook. Now, there may be instances where I add to the OpenStax homework problems if I don't think it's asking really good enough problems or open concept problems. I might add a few questions to that. But for the most part, the homework's going to come from the OpenStax textbook or your Chemistry, a Guided Inquiry workbook. I may supplement that a little bit, but that's all I'm going to do. And again, if you want credit for these questions, put the questions in the question and answers of the channel, not in chat. Okay, so another good question that I got last week was about the difference between mass density and number density in practice. Why does chemistry use mass density rather than, say, number density? And the truth is it really depends on. So there are three densities that are interchangeable in chemistry. And this is getting a little bit ahead because we haven't even talked about units yet, unit conversion, but I do want to go ahead and answer this question. But there are three densities that we use in chemistry as a whole. So we use number density, which we just tend to put as rho. Um, and this is particles, where particle can be anything per, generally for number density, if you're going to use it, it's going to be per cubic centimeter. And we'll talk about what cubic centimeter is later. Then we have what's called mole density, which I'm always going to write as a rho sub n. This is moles, which is a concept we haven't covered yet, so don't panic on that. Per milliliter or liter. It depends on, at that point, what the moles are. And then there is mass density. And some books will write this as D instead of rho sub m. And this is grams per milliliter in general. Sometimes you'll see it in grams per liter, but usually grams per liter is actually going to be a concentration. It's going to be what's called a mass volume concentration unit, not a density unit. Usually for density, mass density, it's going to be grams per milliliter. And that's because, generally speaking, okay, what was asked is why do we have multiple units and why do we use them? We tend to use mass density because you might be told in an experiment you need 1 gram of something, but the something is a liquid. And at that point, it can be very handy to have the mass density, because mass density is how you convert, for a neat, pure liquid, how you convert volume to mass. Now, for a lot of organic experiments, they tell you the number of moles you need, not the mass that you need. So, like if you're reading an organic research paper, it'll say add 0.5 moles of this to 0.5 moles of this. And both of the thises are liquids. And at that point, you really need mole density, because then you know how much volume to add. But usually on a bottle, an organic chemical bottle that's a liquid, it's going to provide mass density, not mole density. So you're going to have to convert. So anyway, that's answer to his question, and that's getting a little ahead of ourselves in terms of what we're covering, but it does allow us to talk about what we need to cover today. And so it's a good starting point, in other words, for what we are going to cover today. Sorry, I got to grab my notes, which are down on the floor at my feet, because I have limited space on my desk right now. Okay. So last time we talked about properties of matter, the solving properties, and that's why we ended up talking about density. Now, because of physical and chemical properties. And the issue with density, and one of the reasons why density is such an important thing, is notice it's a ratio. It's grams per volume. Now here's the truth about all of these densities. The top, so just as a reminder for a fraction or a ratio, you can use those words interchangeably. We have a numerator divided by a denominator. The reason why the numerator is called the numerator because it's how many things you have. The denominator is called the denominator because it is what's my scale. for those things. Generally speaking, mathematically, that's why those are divided that way. Now, in this case, the numerator is either particles, number of particles, which is usually denoted by a capital N, moles, which is usually denoted by a lowercase n, or mass, which is usually denoted in an equation by lowercase m. Now, here's one of the problems we got. Lowercase m is used for a whole bunch of other things. So you're going to have to learn in context if m stands for mass or something else. But in an equation, m is usually going to be mass. And then the denominator is volume for density. Now, the top part, all of these values, n, or m, are all dependent on the amount. You have. So that can be a real issue because I can be holding, you're gonna have to pardon the dirt. Here's a fork and a spoon. Whoop, camera. Are these made from the same material? Well, they're different sizes, so they're going to have different masses. So I'm not going to be able to determine are these made from the same material just by weighing them. Now, the volume is also dependent on the amount that I have. Unless you're talking about a gas. But the volume that a particular thing takes up, generally speaking, if it completely fills the volume, it generally is proportional to the amount you have. And that's true for gas too. You just have to have other things that define a gas. And those things also define a liquid, we just don't think about it. So generally speaking, volume is somewhat dependent on the amount you have at fixed pressure. Let's do it this way, at fixed pressure. Then that is absolutely true. So that's how I fix that where it's true. Pressure volume, P times V. It's generally dependent on the amount you have. But if I fix the pressure 1 bar, 1 atmosphere, then the volume is dependent on the amount that I have. And so that means that, again, I cannot really just use volume to talk about an item. And these two properties are what are called extensive. These 4 properties, actually, are what are called extensive properties. And that's because they depend on how much you have. Okay? So extensive properties depend on how much you have. Now, you just saw me reach behind me to grab my phone. And I just grabbed my phone because I promised you guys that I would leave the chat open to Teams, so that if you wish to ask a question through the question and answers channel of the team. Now, when you have your phone, and you first load Teams, that's what loads up, and it's the chat. If you actually want to find the team for the course, you need to go down to the bottom and find Teams. And if it doesn't show up at the bottom of your screen, hit the little 3 buttons and it'll be there. So then you'll see something that looks like this. And then when you click your team, you'll see something that looks like that. And you'll see the channels on the list below. And if I click on one of the channels, then I can ask questions. So that's how you navigate it through Teams. And then you can just click the little blue icon at the bottom. That's your little write a post icon, and that's how you ask questions. Okay, so these are extensive properties. And what extensive means is it depends on the size of how much you have or the size of the object. Volume, obviously this coffee cup has a different volume than this mug. So these are size dependent. They're dependent upon the thing that you have. Now, the nice thing is sometimes if you take a ratio, that independence goes away. Not always, but sometimes. So intensive properties are independent of amount, and because they're independent of how much you have, they tend to be used as ways to define a compound, ways to define or distinguish a compound or alloy. So when you have something that's independent of size, it can be a really nice way of defining what you have. So if I were to have a bar of titanium, and please remind me and I'll try to bring some in for you guys to see on Wednesday. But if I have a bar of titanium and a bar of aluminum and a bar of stainless steel, if you visually look at them, you're not going to be able to tell them apart. They're all gray. They're all shiny because they're all metals. So they look the same. You're not going to be able to tell them apart. But the moment you hold them in your hands, you can tell this one's heavier than this one, which is heavier than this one, even though the bars are the same size. And that's because the density of those bars are different. Now, what makes them different? I mean, that would be the obvious thing. Well, wait a minute, they're all solids, so why do solids have different densities? And that's because titanium, steel, which is iron, chromium, copper mixture, and aluminum are very different size elements, physical size. So if I look at a single atom of aluminum, it's different size than a single atom of titanium. But they also have, because they have different numbers of electrons, they interact with each other differently as they condense into a liquid and then into a solid lattice structure. And that interaction creates spacing between the elements in the solid. So, this is an interesting thought process and something you really need to sit down and think about. We are in air, right? We're all standing around in air. And when we move our hands, we can feel wind. And when we stand outside in the air and the wind's blowing, we can really feel wind. or when we have a fan or we fan ourselves with paper. All of this may happen because the room may be hot. All of this we can feel. But what are we feeling? In other words, what's the dominant thing in air? So if you're curious, the density of air at one bar, 300 Kelvin. So at 25 degrees C, which is room temperature, 1 bar, that's standard pressure. The density of air is 0.04 moles per liter. And that means that that is I got to get calculator real quick. So that's about where to go? 2.4 times 10. That seems. Oh, that's right. 22 particles per liter, which seems like a lot. So, but it's really, a liter's kind of a big volume, and that's really not that many particles. To give you a sense, liquid water, so to give you a sense of size difference, liquid water is 1 gram per milliliter, which is 0.05 0.056 moles per milliliter, or 56 moles per liter, because there's 1,000 milliliters in 1 liter. So notice the size difference here. So liquid water has basically 56 moles of water per liter, whereas air has 0.04 moles of molecules per liter. And this means that you're looking at, and just so you know, this is roughly 3.1 times 10 to the 25 water molecules and we'll get where all of you guys can do this. So in other words, liquids are 3 3 to 5 times. 5 times is a better measure of that. Have 3 to 5 orders of magnitude. That means powers of 10 amounts of molecules or particles than a gas does. And yet we can still feel that gas. But what's in between the gas molecules? What's in between the water molecules in that volume? What's in between the atoms in a solid? What exists in that region between the atoms in any phase? And the reason why I'm willing to wait while you think about that is this is a hard concept. We are actually at our break count, so while we're taking a short break on me talking, think about that and pop the answer in the live chat or in the question and answers. So the question is, I want to put this in chat because it's an important question. What exists between the atoms or molecules or particles in a gas or liquid or solid? So what exists? If I could microscopically, if I had a good enough microscope where I could literally see between two atoms or molecules or particles, what's there? No bonds, not between particles. The particles are floating free. They are not bonded to each other. And they're not charged, so you don't have Coulomb interactions. What is space? In other words, what exists in space? If I were to go out into the realm of space, what exists? Nope, no bonds. No shells. No atoms. I'm asking what exists between the atoms. No molecules. No molecules. And no electrons. If electrons existed between the atoms, we'd be shocked all the time. No energy either. So the answer to that question is nothing. And see, that's what we struggle with as humans. Nope, no nucleus. No forces. Well, no forces. I mean, gravity's technically everywhere, but it's, yeah, just nothing. Exactly. Vacuum. Empty space. There's nothing between the atoms. In air, in gas, in liquids, in solids. And that's why there's a difference in density. As a lattice forms, and there's a link pinned at the top of the live chat. There's also a link in the classwork for check-in under Chemical Literacy Module 1. It says Lecture 3 check-in. So anyway, we struggle with the idea of nothing. I mean, absolute nothing. And that's because when we look around, we see things. There's stuff everywhere. I mean, in my house, there's stuff really everywhere. So we really struggle mentally to picture nothing. In fact, that's such a fundamental struggle that the whole idea in Buddhism of enlightenment is nothing. It's a mu, I think is what's said in Japanese, but it's a circle with nothing in it. So we struggle with the idea of nothing. And that's why I asked that question that way. But in essence, when things begin to interact with each other based on a whole bunch of stuff in quantum mechanics that we are not going to cover this semester or until you're a graduate student, when things begin to interact, there are ideal spacing for each and every element has this, and each and every molecule and each and everything has this kind of ideal spacing that it wants to be energetically, that minimizes the Coulomb energies and so on and so forth for a given phase. And in between those spaces, there's nothing. And that's why we have different densities, different numbers of particles per volume for different elements. And that's why we can use density to characterize different elements. Aluminum has a different density than titanium because there is a different amount of nothingness between the aluminum atoms in the metallic lattice in comparison to the titanium atoms in a metallic lattice. Why? Because energetically they just interact. The energy of interaction is at the perfect spot when those atoms are a certain spacing apart. And that's nature, God, give it whatever you want to give it. This is an instance where there comes a point, even in science, where you can ask a question where the answer is nature or as God intended. Just depends on your own concept of spirituality, your own concept of the world view. You can interpret that how you want to, in other words. So that's going to depend on who you are. Air is not nothing. That's correct. Air does not qualify as nothing because it's truly not an empty space. It has the air between me and my screen. My screen's about, I'd say maybe 2 feet from me. It's a big screen, 20-inch screen. So, you know, that's a big volume. It's definitely more than a liter of volume between me and my screen. So that means I'm, you know, there's 2.4 times 10 to the 22 air molecules, which means mostly nitrogen, some oxygen, a little CO2 and water, maybe a little argon, between me and you guys and the screen that I'm looking at to talk to you guys. So that seems like a lot of particles. Oh my God. But it's not as much as in my tea, because this is water, and water, you know, my tea is water, so it has 3 times 10 to the 25 particles per liter. This is not a liter of tea. But nothing is nothing. There is nothing in it. Air is not nothing. Air is something. I can take this air, I could take the air right here and put it in a container and put it under pressure and cool it down, and I would form a liquid. So it's not nothing. There is something. And that's why we feel wind. The wind is the pressure of the change in pressure of molecules hitting our skin, and our body interprets that as wind. If there was nothing in air, there would be no wind. A fan doesn't work in space. In other words, a fan doesn't blow particles. We don't feel airflow with a fan if we're in the vacuum of space. Of course, we're not breathing either. But the vacuum of space is as close as you're going to get to nothing. And if you're really going to do that, you'd have to get past the heliopause of the sun. So you'd have to be out where Voyager is right now. To truly get to nothing, you need to be where Voyager is. Because even in the vacuum of space, number of particles in helio. What's the density? Density of vacuum in heliopause. We have about 0.1 particles per cubic centimeter in the solar system vacuum. So, which is called the heliopause, for those of you that are not. So, in the heliopause, which means in the region of space that that the particles of our sun go out into, the vacuum is approximately 0.1 particle per milliliter. So, not a lot, but still something. We know most of the elements. We don't know about dark matter yet, but that's a completely different topic. We won't get into that. Somebody asked in the live chat, since I'm not going over all the materials for chemistry, does CHEM required book, Chemistry, a Guided Inquiry, cover everything that will be on the exam? No. The Guided Inquiry is a workbook. It will provide activities that you will do to help you master the material in your textbook. Your textbook, you can use any textbook you want. I have provided a free version of your textbook. That free version of your textbook is in Teams. It has chapters. You can read the chapters. And I just assigned a set of homework from the first chapter. The exam will be from that homework and the material in Chemistry, a Guided Inquiry workbook. Are we clear? Okay. So, anyway, is important. We have a lot of concepts that we develop because of how we interact with the world. And it's really kind of important to understand that those concepts of how we interact with the world are built upon our body's experience of the world. And that even means, like, even our concepts of color. Like, I'm females. Most females have a better, more nuanced version of colors than a lot of males. People who are red-green colorblind, they don't really see red and green, so they don't really have a concept of what red looks like and what green looks like, because they haven't seen it the way a person that's not colorblind sees it. So a lot of what we define and call and do is because we name it that way, and it's how our body perceives it. And so, how do I know that my red is your red? In other words, here's a marker. There's a top. I'm going to call that top green. How do I know this is green? Well, we all had the same colors when we were coloring as kids. And it's not green in French. It's verde. And I don't know exactly what shade of green it is. So, I don't know. And in the Eastern, there are symbols. There are, characters, Chinese characters that symbolize different shades of green. And I'm sure they have special meanings. So Bia, look at the top of the live chat go all the way to the top of the live chat in YouTube, and you will see the link to the check-in button. And right click on it so it doesn't throw you out of YouTube. Okay, so a lot of our concepts of, it's also linked in Teams. So since I have a person that really is anxious, except you've already missed the timing for check-in, but I will remind everybody, since I've got everybody, that the easiest and fastest way to get to check-in for this lecture is to go to your module. We are on Module 1, Chapter 1, Essential Ideas. Go to where it says Lecture 3 Check-in and check in. Just click on it. Except for some reason it still says forms not accepting. Oh, of course it's not accepting responses. I'm going to turn back on the responses to that form and give you just a little bit more time. But in the future, that form will only be on until 8:30, and then it will turn off. Okay, you should be able to check in. Okay, so that's how you get to check in. Link or down here, but you have to do it by 8:30. Now back to this. So generally speaking, our preconceived notions of the world come because of how we interact with the world. So that's something, when you start talking about this scientifically, you need to be aware of. So science is our way of talking about the world and about explaining it, but there is an inherent bias in that because we are the species interacting with the world. And part of what you learn as you continue to do science is how to try to remove as much of that bias as possible, which is hard. Okay. Now, want to go ahead, we've already talked about the phases, gases, liquids, solids. These are linked to each other. There's a certain language associated with these different phases, and also with transitioning between these phases. We'll talk about this in a lot more detail in the future, but if I'm taking a gas to a liquid, we call this condensation. If I'm taking a liquid to a gas, we call this vaporization. In other words, right now what we're learning is the language, not exactly how this happens or the energy associated with it. If I go from a liquid to a solid, this is freezing. That really should be in red. If I go from a solid to a liquid, that's melting. And now here's the ones you maybe aren't as familiar with. If I go from a gas to a solid, this is called deposition. If I go from a solid to a gas, it's called sublimation. Now, in the Gobi Desert, where the air is uber dry, occasionally you still get snow. That snow comes because you get a little bit of moisture over the Himalaya mountains into the Gobi Desert, and so it snows. It's because it's cold and it's winter. But because the air is so dry and the pressure is so low because you are on a mountain plateau in the Himalayas, the snow does not melt. It sublimes. It goes from solid snow into the gas phase, water vapor. It doesn't actually go from solid to liquid to gas. And that's a combination of the dryness of the air, of the altitude that you're at in the Gobi Desert. That's one of the few places where that happens. Where you may be more familiar with sublimation is dry ice. If you've ever played with dry ice, that is solid carbon dioxide. It's really cold, but when it goes away, it doesn't melt. You don't get liquid carbon dioxide. It just goes away. You had a solid, it was a white solid, and then you don't have a solid anymore. Where'd it go? Well, carbon dioxide is really unique because it absolutely, all of the time, sublimes when you have solid carbon dioxide. The only way you can get to liquid carbon dioxide is you have to be under pressure. I think it's like 10 bar, 7 bars, somewhere in there. And then the solid will go to liquid before it goes to gas. So carbon dioxide's kind of strange that way. And that's why we have dry ice. And that's why it's called dry ice, is because the solid disappears without forming a liquid first. So that's kind of the interaction. You may have also heard of deposition because there is a technique for like growing diamonds called CVD, and this is chemical vapor deposition. And that's one of the ways we can lab grow diamonds today. But it's just basically we take carbon, we take graphite, we heat the bejesus out of it to form graphite in the air, to form vapor phase carbon. And then as it slowly cools under high pressure, it will condense, it will deposit on a surface that's cooled in the form of a diamond. That is chemical vapor deposition. And we use that quite frequently. Okay, now, been very careful, haven't drawn anything, which is really hard for chemists because as chemists we draw all of the time. It's just what we do. We draw things. It's an inherent part of chemistry. So there are different ways of writing a molecule. And I'm going to use a molecule you guys are familiar with, i.e. ethanol, drinking alcohol. So ethanol I could represent as C2H6O. And this is something called a molecular formula. And in all honesty, it's not particularly useful because there are other compounds that have that same formula. Another compound that has that same formula is dimethyl ether. Has that exact same molecular formula. So that depiction of a molecule tells me how many carbons, hydrogens, and oxygens are in it, but it doesn't tell me anything more about the system. Now, I could do what's called an extended molecular formula. Which I would then write as CH3CH2OH. This would be for ethanol. Dimethyl ether would be CH3OCH3. The extended molecular formula shows me a little bit more about the compound, because what it begins to show me is how, and technically for the extended molecular formula, I inherently put bonds in there. There we go. It's beginning to show me how stuff is connected. But you have to know how to read this to see how stuff is connected. So we might also write what's called a structural formula. So that would be, and it's rare you're going to see a chemist write this way, because it takes time. So, and you see, so that's the structural formula for ethanol. And that's the structural formula for dimethyl ether. And generally speaking, we don't ever as functioning active chemists write structural formulas that way. What we'll do is we'll write a condensed structural formula. carbon. That would be the one for ethanol. And this would be the one for dimethyl ether. Notice in the condensed structural formula, basically we don't show the bonds between the central atom. Carbon here is the central atom for this particular structure. Carbon is the central atom. So if you look at dimethyl ether, I could either consider oxygen as the central atom, or I could and it's kind of central to the entire molecule, or I could look at carbon as the central this first carbon as the central atom, this first carbon as the central atom to these other four. This carbon is the central atom to these four, and oxygen is the central atom to these two carbons. So we use central atom as a concept when we start talking about structure and shape, but that central atom is for a cluster in terms of bonding. So it's again, it's one of those guiding concepts that you have to use as a guide, but not religiously, because when you have more than one atom bonded to each other that's then bonded to another atom, then it's a more complicated thing than just I have one atom with multiple bonds around it. Now, it's very common to see condensed structural formulas or a mixture of condensed structural formulas and structural formulas, especially in organic chemistry. You're going to write a condensed structural formula, but you might show one of the hydrogen bonds because that's the one you're about to break or pull the hydrogen off of. So you'll tend to emphasize the bonds that are undergoing reactions and de-emphasize everything else. So generally speaking, you'll have a kind of a blend of those two. Now, there are ball and stick models and space filling models. We don't draw those at all. You have to have a computer to draw those, and even then, you're generally not going to show them. So ball and stick models are really, really useful. And one of the things I highly recommend you invest in is what's called a chemical model kit. This will be very helpful in organic chemistry, but it's just not something we draw on the board because it's hard. But the other way we draw this is called the wire diagram. And this is the most common way you're going to see organics drawn. So in the wire diagram, that's ethanol. And this is dimethyl ether. So in the wire diagram, you're showing the bonds. You never show hydrogen. Carbons are not, the C for carbon is actually not written down. So this, every place that there's, so right there and right there is a carbon, right there and right there is a carbon. So the place where the lines end or intersect that doesn't have an atom other than carbon is a carbon. And that's quite common, wire diagrams. And in fact, pretty much as soon as you hit organic chemistry, that's how molecules are going to be drawn. So during this semester, I will start at the beginning of the semester, after we've covered structure, drawing wire diagrams and also either a condensed structural formula or a molecular formula. And then as the semester progresses, I'll wean you off of the structural and molecular formulas to predominantly wire diagrams. And the reason why I do that is because that gets you used to seeing the wire diagrams and interpreting them so that when you move on to Gen Chem 2 and Orgo 1 and Biochem and molecular biology, you're already ready and prepared to interpret these as molecular structures, because that's the more common form. Now, these are all molecules, and they're all molecules because they are covalently bonded. And that's the big deal about molecules. So, I'm going to pause for just a minute. We're at a break. It's 9:30, a little bit over. So I'm going to pause and see if there are any additional questions about the material real quick. So at 9:40 we'll start again. But if you guys have any questions, now's a good time to ask them about how chemists represent molecules. Oh, goody, I can zoom out. So, all of these different ways of representing molecules we will use for different things. The top one is going to be the least common, because they're just, as soon as you get to carbon-containing compounds, there's just too many compounds that can have the same base molecular formula. It just doesn't give you enough information. The only thing that thing's good for is calculating molecular weight. It certainly is easier to calculate a molecular weight from that when it's written that way. But as a functioning working chemist, what are the other most common forms? I would say the extended molecular formula, the condensed structural formula, and the wire diagram. Those are going to be the three, generally speaking, most common ways that we're going to write something. That's a molecule. And so, again, to make a big deal out of these, all of these are molecules because covalent bonds. Okay, so what defines a molecule is covalent bonding. Now, compounds, all molecules are compounds. Compounds are a collection of atoms correlated to each other so that means no random motion, or well, I can't quite put it that way. So correlated to each other through a force. That's kind of a general definition of a compound. So, sodium chloride is a very good example of a compound that we use all the time. It's table salt. This is a compound. It consists of sodium plus, chlorine minus, in a lattice structure. Drawing this is entertaining. I'm going to do my best to draw it for you though. So the way you would draw sodium chloride is, first thing you do is draw a box. To the best of your abilities as an artist. Mine suck. Okay. There is a box. In the center of that box, draw either a sodium or a chlorine. On the corners of the box, draw the other. Now, this box that we've just drawn is like a Lego. This is what's called a unit cell, which apparently I can't write today. And you can kind of view this as a Lego. So we're just going to set that box on top to form a three-dimensional lattice. Now, if I'm looking only inside the box, how many chlorine atoms do I have? So, inside box only, number of chlorines is 1. Inside box only, number of sodiums. Now here's where it gets interesting. The number of sodium atoms inside the box is that little bitty corner right there. That's it. So technically speaking, I have 8 sodium atoms, but only 1/8 of the atom is inside the box. So 1. But it's not just one unique sodium atom. It's technically a portion of 8 sodium atoms that are inside that box that form 1. And that's why sodium chloride, this thing, is called an empirical formula. Not a molecular formula. There are no bonds here. What holds it together? Well, Coulomb interactions hold it together. So this thing is correlated. If I move that chlorine atom, all of the sodium atoms are going to move with it. So all of these things are correlated to each other, but they're not bonded to each other. There isn't an 8th sodium atom near the center of the box. Chlorine's in the center of the box. Oh, sorry, there's 6 and 1/6. Thank you for catching that. There are not 8, there are 6. 1, 2. Oh. 1, 2, 3, 4, 5, 6, 7, 8. Yes, there are 8. I thought so. There's no single sodium atom in that box. Every single sodium atom has a little bit inside that box. Oh, that's what you were asking for. Okay. Sorry about that. Thank you. Thank you for catching that, though. So, empirical ionic compounds, sodium chloride's an ionic compound because it's technically sodium plus chlorine minus. So it's called an ionic compound. Negative sign is an anion. Positive sign is a cation. Okay? It's important. Now, one of the things we will have to learn is what elements on the periodic table tend to form cations, what elements tend to form anions. Luckily, the periodic table helps with that, and that will be chapter 2. Right now, the main thing to recognize is that there's a difference between a compound and a molecule, and that difference is covalent bonding. And a really good example of that is DNA. So DNA, all of you, as soon as I say DNA, probably have a picture of this double helix structure in your head. And that's why it's a really good example. Is today we have an amazing idea of what DNA looks like. Now, DNA is actually composed of 2 strands that are lined up kind of mirror image to each other. And those 2 strands are separate molecules. So this strand has it's a very long, big, heavy, lots of bonds, but it's all covalently bonded. This strand, also long, all covalently bonded. When the 2 strands come together, they interact through hydrogen bonding. And hydrogen bonding is just a correlation. It's a lot like ionic bonding. It's not a covalent bond. It's easy to come apart. It's easy to put back together again. Water is hydrogen bonded, liquid water. That hydrogen bonding is what holds those 2 strands of DNA together. So DNA, double-stranded DNA, is a compound, not a molecule. It's a compound composed of 2 molecules. Each strand of DNA is its separate molecule. This is really important in terms of our body, because if double-stranded DNA were a molecule, we couldn't duplicate it the way we do. See, it takes very little energy to break those hydrogen bonds. So we can go through, and we have a little enzyme that does this, that unzips the DNA, that pulls the hydrogen bonds apart, and that opens the DNA up and allows for replication. And then as that molecule passes, those hydrogen bonds come back and re-interact with each other and reform. If it were covalent bonds, that little enzyme wouldn't have enough energy to break them, because it takes so much energy to break a covalent bond. So our entire biochemistry, our entire body's chemistry, relies on the fact that there is a distinct difference between molecules and compounds, and that difference is covalent bonding. Could not do most of the body's chemistry if everything was covalently bonded. So that's an incredibly important concept, the difference between a compound and a molecule. And it's commonly misused. I postdoced in a physics department. When I was a postdoc, the big, just won a Nobel Prize, big research, active orientation. In other words, the big deal that everybody was talking about was something called Bose-Einstein condensates. We'll talk about a little bit about what makes a Bose-Einstein condensate in chapter 2 and chapter 3. Mostly chapter 3. But anyway, Bose-Einstein condensates, and there were a whole bunch of talks at a seminar I went to of we form molecules in Bose-Einstein condensates. And I thought, oh, cool, that'll be really fascinating. And so I went to it. And I sat through that entire talk and thought, no, you didn't form a molecule. You formed a compound, yeah, but not a molecule. So at the end of that talk, one of the young faculty members at the University of Virginia Physics Department was there, and I'm like, you're not forming molecules. It's like, what? No, they interact. I'm like, yeah, they interact. You're forming what's called a compound. That's not a molecule. It's not covalently bonded. It's like, oh, I didn't know there was a difference. So that's the issue. So Valerie, your question. There is a course calendar in Teams. Technically for this course, as much as possible, we will be online, YouTube live stream on Monday mornings, 8 to 10 a.m. We will be in person as much as feasibly possible on Wednesday nights, 6:30 to 8:30 p.m. There are instances, because I have to be out of town, when we will also be online on Wednesday. And those instances are in the course calendar. Now, I teach also Gen Chem 2. So like tonight from 6:30 to 8:30, I will be teaching in person, but that will be General Chemistry 2 at Queens College. And then General Chemistry 2 will meet on Wednesday mornings from 8 a.m. to 10 a.m. Online. So it's just the opposite of your schedule. So Gen Chem 1 and Gen Chem 2 have opposite schedules. Now, Tuesday, Thursday from 8 p.m. to 11 p.m., I will be at the computer with a YouTube live stream active that anybody can tune into. All I'm going to be doing is typing, listening to some music, typing, doing what? Coursework, typing homework problems, typing exam questions, typing quizzes, preparing for the course. Are you supposed to be in Gen Chem 2? Let me check that. No, I put you in Gen Chem 2. I put a link in my Gen Chem 2 course to Gen Chem 1 because we are reviewing nomenclature and structure in Gen Chem 2. So I went ahead and provided a link to the Gen Chem 1 course in case you wanted to tune in. But no, you are in Gen Chem 2. But right now in Gen Chem 2, we are reviewing Gen Chem 1 material. But there were some students who were uncertain of their nomenclature from Gen Chem 1 because it had been several years since they took Gen Chem 1. So I put in a link for Gen Chem 2. Yes, we're meeting in person tonight for Gen Chem 2. 6:30 tonight. See you in class. Other questions? So this is a really good time and a final time that I will entertain questions that I've covered in lectures 1 and 2 about how the course is set up. I will again reiterate that, well, for you guys, since I just put it up, if you want to know what will be on the final examination, if you go to the course policy book, which I will make a PDF of so it's easier to access, in the course policy book, under course learning goals and objectives, you will see a list of learning goals. So students will learn how to analyze and express experimental results. This includes convey measurement uncertainty in terms of both precision and accuracy, accurately write measurements with appropriate significant figures and correct units, and accurately convert values from one set. These are, we literally take these learning goals and write exam questions. We try to aim for one exam question per learning goal. There are not 50 learning goals, so sometimes there will be some questions where you have 2 questions per learning goal. But these are the learning goals for the course. If it says optional, it will not be on the final exam. Look, in terms of homework questions, I'm going to ask the questions. I have a limited number of questions I'm going to ask you. So most of the questions I'm going to ask you are going to be multi-concept questions where I can hit multiple sections in one question, because that just makes it easier. I may take multiple questions and combine them into a single question from that suggested homework list, but it will come from that suggested homework list. I am supposed to provide you, as it states in that policy book, as a requirement, legal requirement for the state of New York, I am supposed to provide you 180 hours of learning. Now, I'm doing some of that by homework sets, and I posted 100 homework problems today. How many of those problems you need to work to understand the material, I don't know. Each one of you is a different person. Some of you are going to learn the material from chapter 1 really quickly. And then when we get to chapter 3, oh my God, you're going to struggle like crazy. Others of you are going to struggle with the material from chapter 1, but by the time you get to chapter 3, you got it. I can't judge that. It's really going to depend on you, who you are as a person. How rapidly do you recognize patterns? Do you memorize definitions better than you do problem solving? There's so many factors. Every one of you is a unique individual person. You work homework until you get it. How do you know you got it? When all of the problems feel the same, you don't get nervous when you're approaching a problem, you got it. You're going to submit homework. I'm going to, on Wednesday when we meet in person, I'm going to come in with a sheet of paper that says, for exercise, whatever random exercise I picked, what is this? What is this? What is this? From that exercise. So if you've worked that exercise, you've already got the answers, you just write them down. If you haven't worked that particular exercise, but you've worked similar exercise, you should be able to work that homework problem in the hour that I give you in class to work it. And then you turn it in to me at the end of class. No, you will. The 100 homework problems, I'm not grading 100 homework problems. Now, what I am going to do is provide a solution or answers to those 100 homework problems so you can grade your own. But I will be grading selections, randomly chosen selections of those 100 homework problems that you will submit. It's not technically a quiz because it's open notes. So what I suggest doing is get a composition notebook and work homework problems out of it. How am I going to approach working those homework problems? I'm going to approach it by random number draw. I shared a random number site in the first homework. What I would suggest doing as a way of studying for this course and approaching, oh my God, 100 homework problems. How am I going to do that? Do 10 a day. Just randomly pick 10 homework problems a day. In 5 days, you've worked 50 problems. If you want to work all 100, randomly select 20 problems per day, but that's a lot. And the truth is I don't think any of you need to work all of those problems because a lot of them kind of repeat each other. Yes, Open Notes includes digital notes, but not digital. So you can load your OneNote notebook or your digital notebook, but you must have your iPad or your computer in airplane mode. So you must have your digital notes downloaded to your iPad where you can access them. But in other words, if I walk by and you're using ChatGPT to do your homework, I will take it up from you and you earned a 0 on that homework in class. And if I have a strong suspicion that you used AI to do your homework, if you took it home with you and you're going to submit it late, and I have a strong suspicion you used AI to do your homework, I'm not going to bring you up on academic dishonesty charges. I can't do that because I can't prove it. But what I will do is put you on the department list of people who I suspect are using AI, and that will impact, do you get recommended for positions in research labs, and do you get, if you come and ask for a letter of recommendation, will you get one? So, if you are going to do your homework and not submit it in class, i.e. you're going to do your homework late, don't use AI. Now, how am I going to, quote, suspect you used AI? If you're making 100% on your homework and you make a 10% on the first exam, you didn't do your homework. Does that make sense? Now notice I didn't say you had to make 100 on your exam, but most people that do their homework are going to make a 50 or above on their exams. If you make below a 50 on your exams but you made 100 on your homework, no way. No way you can do that. Now, somebody asked about cheat sheets. I'm going to reiterate. You're allowed your data book. You're allowed whatever notes you wrote in your data book on exams. You are not allowed a separate sheet of paper from your data book. So it's whatever notes you wrote in your data book. That's it. So no separate paper, no open notes, just what's in your data book. Other questions? Okie dokie.